Hello, everyone, and thank you for joining us today. Welcome to Megger's monthly webinar series. Today's topic is the best practices for performing travel measurements on HV circuit breakers. And can you go to the next slide, please?
It should be not switching.
Yeah.
My bad. Screen is paused.
No problem. All right, and my name is Jamie Smith, and I'm the Digital Marketing Specialist for Megger North America, and I'll be acting as the moderator for today's presentation. I'll also be supporting you on any technical issues or questions for our presenter during the session. And as you can see on the right side of your screen, there's a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will be reading those questions out after the webinar is concluded. We'll have 30 minutes to go over those questions that you have. You'll also receive a copy of the presentation afterwards and a link to the recording session if you want to watch it again or share it with your colleagues. Please give us a day or two to get you that presentation, and that'll be emailed to you. Remember, you can also ask questions at any time, and we will get those questions answered, as many as possible, at the end of the webinar. Our presenter today is Robert Foster, and he's an application engineer for Megger. Thank you for joining us, Robert.
Yep, no problem. Thanks for having me. I guess we can go ahead and get started. Sorry about the technical difficulties at the beginning. So I will go through, and this is just a basic outline of what we'll be talking about. We went through the introductions, but I'll just kind of reiterate. This is basically on how to connect your transducer, what to do when you're, not sure. Hopefully the manufacturer can provide some information. But I'm going to go through just in the beginning. I'll talk briefly about why the transducer is important, why you should be making travel measurements, and then we'll focus on the types of transducers. I'll go through a bunch of different connection examples. I'll talk about your conversion factor, conversion table, like your transfer function kind of deal. And then I'll go through, and I actually did a case study on a Siemens SDS2 breaker where I hooked multiple transducers to different parts to see if I could replicate what I'm getting, if I use the right conversion table. And then I'll have some recommendations what to do when no information is given. And then we'll go through some concluding remarks afterwards. And then, of course, your question and answers after that. So just generally on circuit breakers, they really, sometimes they're neglected, and they shouldn't be, because they protect the valuable assets in your substation. You don't want your $5 million transformer to blow up because you didn't maintain your circuit breaker. So you want to make sure that these things are in tip-top shape, because the weird thing about a circuit breaker is it'll sit there idle for, like, it could even be years. And it's going to be a perfect conductor during that time. And then all of a sudden, a fault comes through, and nearly instantaneously it needs to go from a perfect conductor to a perfect insulator and clear a fault in the meantime. So it really needs to be maintained, because it's only called on to act for milliseconds, but it needs to be able to perform flawlessly during that time. And if you look at IEEE, they call it a mechanical switching device. It's really just, an open-close device. And then if you look at some SIGRAE studies, you'll see they've gone through and they surveyed a bunch of different utilities and everything, and they found that 50% of the major failures of a circuit breaker are due to this operating mechanism, and 30% are due to like the electrical control circuits or auxiliary circuits and everything. So if you look at this, this is the type of information that will be revealed by time and travel measurements. And so not just timing, but as we said, travel measurements, your transducer. So travel reveals much more than just your timing and your coil current measurements. So now we're talking about motion. So what kind of parameters are derived from motion measurements? For one thing, you're going to verify the stroke of this interrupter. And then from that, you can also get the velocity of the interrupter. And velocity is important because it needs to be sufficient to extinguish that arc. You can have something where your signal comes in late, or let's say your coil's bad, so it kind of takes a little bit longer to trip. But as long as it releases that trip latch and that spring or whatever and that mechanism gets going, as long as you have enough velocity in while during that interruption, you're going to be able to extinguish that arc. So you want to make sure you're measuring that velocity, and a lot of times you'll go to manufacturers and they're not really cared about the times, they're cared about the velocities of that circuit breaker. So we can also look at and verify your contact wipe to make sure that enough of the contacts are connected there. You'll see that it verifies the proper operation of the dash pot. If you have this dash pot in there, because on that opening, the velocities are very fast, that there's a lot of energy being dispersed from that mechanism. And so if you have too little damping, you can overshoot it and be busting apart that interrupter. And then, of course, if you have too much damping, you could end up to where it'll hit and bounce back, and you could have some kind of a restrict or slow it down in the arcing zone. But again, that velocity is what you need to interrupt that arc. And then some other applications, in combination with a dynamic resistance box or something, you can do your dynamic resistance measurements with velocities with the transducer to evaluate the arcing contact length of your SF6 circuit breakers. So when we're talking about the transducer, really stroke is the basis for all the measurements. So you're going to hook up this transducer, and you're going to see the difference between open, close, and get that stroke. Then we can also see how far it overshot for over travel, rebound, and some of those parameters. But then you also have some parameters that are dependent on both the stroke and the times, or the stroke and the contact touch that you're going to be measuring. So these will be things of penetration or wipe, your velocities, and your damping. So if you look at this, you'll see, okay, a standard close-open response of a circuit breaker here with your motion measurements. And if you look down at the bottom, the way we do timing is we give you a thin and thick line. So a thin line is open, and a thick line is closed. So you can see starting from the left of those bottom three lines, your breaker starts, it's open, eventually it comes closed, it's closed for a short amount of time, and then it opens up again. Now if you look at the kind of the y-axis and you see that curve that comes up, you'll see there's a resting position when it's open and a resting position when it's closed. So the difference between that resting open position and that resting closed position is the stroke of your circuit breaker. And then you'll see a few other things, like on the top here, you'll see over travel. So really over travel is how far it goes past that resting closed position on the close. And so you'll measure from the resting closed position to how far past it goes, and that'll give you your over travel measurement. And you can also have an over travel on the opening as well. And then if we follow the curve past that over travel, go back down, all the way down coming open, and you'll see it'll go into that damping zone, and it over travels there, as I said, on the opening, and then it bounces back and goes underneath the resting open position. that's what we call rebound. So you want to look at both over travel and rebound. If over travel is going too much, you can do damage to the interrupter. If rebound happens too much, you may have a restrike or something like that. Some other things you'll see is up on the upper left in blue there, you'll see that contact penetration. So what that is measured from is when your contacts first touch to the resting closed position. So that shows you how much you have contacted in there to make sure, you know, that enough of these are engaged, enough of the contacts engaged for ample current flow there. If it's a vacuum breaker, really you don't have any contact penetration or wipe, but an oil circuit breaker, SF6 circuit breaker, you'll have these at least maybe like anywhere from 10 to 30 millimeters or more with an oil circuit breaker. Some other things that you'll see, as I said, velocities are very important. So if you look, there's 4 points on here, and those are your speed calculation points. And so we want to get the stroke and over travels and all that, but really we also want to get the velocity of these circuit breakers. And sometimes you'll hear a time and travel device referred to as a speed tester, because that's what they're looking for, is how fast their interrupters are traveling. So what you do is you look at these points, and you want to find some points that are on the linear portion of the curve, but also important is to be in that arcing zone on that open. So when you're opening that circuit breaker, you'll see, okay, at some point the contacts are going to break, and this circuit breaker is going to start arcing, and then eventually that arc will get extinguished, or it'll cross zero and come back and won't be able to restrike. So you want to make sure that the velocity is sufficient enough to extinguish that arc in that arcing zone. So just that was a little background on transducers, why they're important, and what we'll be measuring with them. But now let's look at the different types of the transducers that we may have here. So there are 2 main types, rotary and linear. So a rotary, now you're just measuring and you're outputting a value in angle, typically degrees. Sometimes I have seen it in radians before. And then when you measure with this rotary, you're generally going to use like a conversion constant or table to convert it over to length. If you don't have this, you might just measure in degrees. Sometimes the manufacturer might give you a specification in degrees per stroke, in degrees per second for a velocity, but most of the times you're hoping to get some kind of conversion constant or table. The other one, and the one that we're a lot more familiar with, I'd say in the U.S., because of dead tank breakers and your bulk oil circuit breakers, are linear transducers. So now this one measures in length and outputs a value in length, typically in millimeters or inches. Most modern SF6 breakers, vacuum breakers, they're giving it to you in millimeters, but your old bulk oil circuit breakers mostly are in inches there. And then if you hook direct connect, you don't need any kind of conversion constant, but sometimes you might need a conversion constant or table to convert over as well. And the type of transducer you use depends on the circuit breaker. And you'll see, even though a manufacturer, they recommend a linear to their customers because that's what a lot of people are used to using, but they'll measure with a rotary. Or, if some people are more familiar with rotaries, they might hook up a rotary. So a lot of times you can use one or the other with a certain type of breaker. But generally what I do is I try and follow the manufacturer's recommendations, and then if I select one and I use that on commissioning, for all my future tests, I try and use that same transducer to be consistent and to be able to compare my measurements over time here. So looking at linear transducers, these come in a variety of types and lengths, of course. So I've seen some as small as like 25 millimeters or 1 inch, and then I've seen them up to like a meter or a yard or more for some old oil circuit breakers where you had this phenomenal stroke length that you had to measure. What I generally see is for your medium voltage vacuum type breakers, a 25 or 50 millimeter linear transducer will do, and you want a nice small one to sit in there. And then as you start to get into your SF6 dead tank, usually like a 200 to 300 millimeter transducer is good because your lower, your 72 kVs, your 145 kV circuit breakers, they only have a stroke around 110, 120 millimeters or so. And then as you get up to your 245s, 300s, 500s, they might go up to a 200 millimeter stroke or so. And then, once again, as I mentioned, the old bulk oil circuit breakers, you might need a longer 500, 600 millimeter transducer where they have this 18-inch stroke that interrupters traveling back and forth. And so even though we have different ones here, a linear transducer adequate length will fit a variety of circuit breakers. You could take a 200 or 300 millimeter transducer and hook it up to a vacuum circuit breaker and still measure it. It's just that sometimes physically it's not easy to hook up a larger transducer to it in that small area or small volume that you have inside a vacuum circuit breaker to connect to those contacts. So you'll also see there are special transducers out there that are designed specifically for a mechanism, such as the ABB, HMA, and their newer HMB, where that transducer actually has to go directly in to that mechanism and is a one-to-one with how those interrupters are traveling. So different ways to attach the transducer. If you can, what's nice is you can make it directly to the moving contact via like an operating rod, and now you'll see that whatever that interrupter moves, that transducer will move with it, and from there you'll get an exact one-to-one replication with the stroke and velocities and all that. And a lot of, I'd say most of your bulk oil circuit breakers, although I've seen rotary on those, use that linear where you take this 1032 rod and there's a little device on top of the oil circuit breaker, a little housing that you can take off and screw that 1032 rod straight down on the interrupter itself. Same thing, you'll see it a lot of times on minimum oil circuit breakers where you can hook to the interrupter there. And then some SF6 dead tank breakers, they'll use a linear transducer as well. And most vacuum circuit breakers that I see, people are using a linear transducer, albeit a small one because of that very small stroke of the vacuum bottles. Other things you can do, you can connect it directly to like a transducer to a moving contact, but with angular movement. And I'll have a picture of this a little bit later, but there's an old Westinghouse SFA circuit breaker where you'd have to pull the gas out, open up this tank, and then put a rotary directly to the center, and it would measure along there, and then you convert to get what the interrupter stroke, the arc length stroke was. And then you can do an indirect attachment, but still with a linear transducer, where you might be hooking to a mechanism and then transferring that over to with some kind of conversion factor to get the stroke of the interrupter. And then you could also have it where it's kind of parallel the interrupter, but through a system of linkage, it's mimicking what the interrupter is doing. And then you can also do this with an angular transducer, a rotary transducer, where you have an indirect attachment to get your angular movement, and you're putting on like a gear or a spline or something between the operating rod and the linkage, and then converting it over with the conversion tape. So one thing I'm going to go through in just a moment here and show you different pictures of transducers and attachments, but I just want to make a moment of caution here. Before attaching a transducer, you want to make sure you're safe. There's a lot of energy stored inside these mechanisms. So you want to place that circuit breaker in an open position and then discharge any energy, and sometimes you have to close and open the circuit breaker to discharge this energy. And if you're not able to discharge the energy that's stored in the mechanism, use some kind of maintenance or blocking pins, and of course de-energize control panel. You want to do whatever you can to eliminate this thing operating, because when you're hooking up a transducer, your hands, your appendages are going to be in compromising spots, and if that thing operates, it could spell disaster for you. So just whenever hooking up a transducer, be extra safe, be extra cautious of what's going on around you. So looking at some of our different transducer connections here, you can see on the left, this is your bulk oil circuit breaker, and on top of one of those tanks, we are hooking up a transducer here, a nice linear transducer. So if you zoom in and see on the right, you'll see that that's just right on top of it, and there's a 1032 little piece of all thread that's going down through there and connecting to that circuit breaker. And so as that interrupter of the oil circuit breaker travels up and down, it drives that transducer up and down, and you're getting a one-to-one movement. Whatever that interrupter moves, your transducer's going to move. So as long as that transducer's calibrated, you're going to get the right value there. So that's your bulk oil circuit breaker. Here's a picture of a minimum oil circuit breaker where now we have just a little bit of oil in there. It's a live tank design for oil circuit breakers, but once again, a direct connection with a linear mount. Looking over at an SF6 dead tank circuit breaker, you'll see here that it's an indirect linear measurement. So now we have this gang-operated three-phase breaker, one break per phase. And now, if you look on the right, you'll see there's a little clevis that is actually attached to the main shaft that drives all three interrupters. And then from there, you have this little fork attachment, and you connect to that transducer, and that transducer runs parallel to the interrupter. So even though this is an indirect connection, that little clevis is designed so whatever that interrupter moves in the circuit breaker, that your transducer is going to move and mimic it, so it's also a one-to-one ratio there. So you're getting the exact stroke and the exact velocities and everything of that interrupter. I had mentioned that we have some special circuit breakers or mechanisms really that take, you have to hook up a transducer to them that fits directly inside of that mechanism. So this is one of those. This is the ABB AHMA, and then following that, we have the ABB AHMB. And so these hook up, and it's connected, that actual mechanism is connected directly to the interrupter. So as that interrupter drives in and out, or as that mechanism, I guess, drives in and out, it drives that interrupter in and out, and we're hooking directly to that and measuring the exact stroke of that interrupter and the exact velocities over travel and all the related parameters that go along with the stroke there. This is an example of a vacuum circuit breaker where now we have this little direct connection down on the right below one of the poles. So this is on the outside leg there. So once again, it's gang operated, but this manufacturer puts this little tab so you can hook directly to it and get to, as that vacuum bottle actuates up and down, your transducer will go up and down, and you're getting the exact stroke of that vacuum bottle there. So we've talked about linear transducers here, and now looking at this, you'll see that we're using a rotary transducer. So this is now, once again, an SF6 dead tank circuit breaker. But instead of using a linear transducer, this manufacturer recommends that you use a rotary transducer. And so you use a little attachment here, and we have some bolts that you screw in to one of the splines, and then a little flex coupler. So now what happens is the mechanism is in this cabinet here, and it drives those arms back and forth, and then those rotate the spline, which then reconverts and drives the interrupter in and out to close and open that circuit breaker. So we can hook directly to this spot here and get the angular movement. And then, of course, we're going to need to convert this angular movement over to a linear movement to get our linear values. So this is an SS6 dead tank circuit breaker. But if we come over here and look at a live tank circuit breaker, you see same thing. This is a rotary attachment. So that's that circuit breaker in the center. The mechanism is on the right of that breaker there. And then if we look to the left, we actually have to use a transducer to measure the contact travel, which most people are used to. And so we'll measure it in degrees. And with this particular one, we need a conversion table to convert it over to a linear length. But what's interesting about this breaker is not only do you measure contact travel with the transducer, you're actually going to measure dashpot travel as well to make sure that this thing is damping correctly and meets a couple parameters. So even though this is a gang-operated circuit breaker, you're going to make a measurement with two transducers, one on the contacts and one on the mechanism itself, both rotary there. So we've seen a couple different attachments with both linear and rotary, and so you'll see that sometimes we do a direct attachment, and some of the advantage of this, as I said before, is now you're hooking directly to that interrupter. So whatever that interrupter moves, your transducer is going to move along with it. So you know if my interrupter moved 110 millimeters, then my transducer moved 110 millimeters, so I get the exact stroke of that. I don't need any kind of conversion factor. I don't need any conversion table, and I don't have any kind of outside influence like gears, mechanical plate torsion, messing with my my results. I know exactly what that interrupter is moving. And so with this direct attachment, you calibrate your transducer, get an absolute measurement, and you're ready to go. So with that being said, why don't we always measure direct? I mean, it would be nice. We wouldn't need to know conversion factors and all that. But the problem is it's just not always possible. It depends on the type of breaker. Sometimes with your SF6, you have gas in there. You can't open it up and connect to it. Well, you could, but then now you can't operate at the same speed because that gas acts as a dampener. Same thing, you can't get access to vacuum bottles. On some live tank breakers, you might have 2 brakes per phase. So now it's going to go up, drive through this mechanism linkage or this gear linkage, and then convert like a vertical movement to a horizontal movement, putting those 2 interrupters in and out. So you might need to hook somewhere else and go through linkage just to get the overall movement of this thing.
Hey, Robert.
Yep.
I had a couple questions come in that related to the last couple slides. I was going to see if you don't mind taking the time to just answer those real quickly.
Not at all.
One of them is, okay. One is from Scott, and he asks, can you do this test live? And if so, what would it change the results?
So, okay. So I guess technically you can do this live. Some manufacturers make a like these online monitoring systems, but you have to have your transducer always hooked up. And depending on the type of circuit breaker, if that transducer is sitting on top of the circuit breaker or is up in the air where their parts are live, you really can't have a transducer up there now because it's going to be live, and you can't isolate the cables and all that. So it depends on the type of circuit breaker, but I have seen where people hooked up a rotary transducer somewhere where it's safe, below any of the conducting, or the high voltage parts, and been able to run a test while it's live. But I would say 99.9% of the time, this is an offline test. So you don't really want to be doing that when the circuit breaker is live. I will say, though, because you're measuring how fast it's going and you're just actuating normally, if you did a live test versus an offline test, it's going to behave the same way with as far as motion goes.
Okay. Thank you. And one more question. Can you explain DRM? And is it a part of this test you were discussing or a separate instrument?
So I would say, so DRM stands for dynamic resistance measurements. And so the way I look at this is you're basically giving a micro-ohm measurement while you're operating the circuit breaker. So you use a time and travel device, an analyzer, you hook up your transducer and all that. But in conjunction with that, you use a separate little attachment to your analyzer or attachment piece where you're injecting current now while you're operating the circuit breaker. And what this does is you can see going from when your main contacts are connected, you'll have like a micro-ohm resistance. And then at some point, the main contacts will disconnect, and you'll go to your arcing contact. And so you'll go from like a micro-ohm to a milliohm measurement. And then at some point, you'll go from milliohms to now your arcing contact opens up, and you'll go from milliohms up to infinite ohms or an open circuit breaker. And so this is used to evaluate your arcing contacts on your SF6 circuit breakers. So any like critical SF6 breakers, high fault, especially generator circuit breakers where they're always breaking a lot of current, you're going to want to perform this dynamic resistance measurement on there. But it's an addition to your time and travel measurement where you hook up a little bit of a current injection box and test with that.
Okay. All right. Thanks, Robert. Thank you for your questions, y'all. I do see some other questions coming in. We're going to try to continue the webinar, and we'll get to some of those other ones later after the webinar has concluded. Thanks.
Yep. Sounds good. All right. So a couple options that we have for an indirect motion measurement. You can, if you don't have any kind of conversion factor table, you can go in and hook up this transducer and just measure what you're doing. So you can either get a linear movement or an angular movement, and then you take this and you use it as a fingerprint, and then you reference this for all future measurements. So you go through, all right, this is what we got. Preferably you're doing this during your commissioning test so you know that circuit breaker is in good condition. And then from every test out there, you compare to that original one, see is our stroke varying, our velocities, is any of that stuff changing, over travel, whatever. But if you're just doing an indirect measurement and you don't have conversion tables, you don't have any of that stuff, your strokes, your velocities, these might not be comparable to that factory test report. So if you do this, like I said, you want to make sure you're doing this at in the beginning when you know that circuit breaker is in a good condition. And then, of course, the other option is now you're measuring the travel, at the transducer, but then you convert it. You use a conversion table, a conversion factor, transfer function, whatever. And so it may be a constant conversion or nonlinear conversion where you use the table, but then if you're converting it correctly, your strokes, your velocities, all this stuff should be comparable to your factory report. So a couple different measurement options. Absolute measurement, now your transducer is a reference, and so you present either distance or angle depending on what you get. You can make an absolute measurement and then have a linear conversion factor. And so you can, if you measure in distance, you can convert it to distance, just like a multiplication factor, or same thing with angle. Or you can make an absolute measurement with a conversion table. So now you can measure with a linear or a rotary transducer and then convert it over to a linear movement. And then you can also do a relative measurement where you hook up this transducer and you physically measure the stroke, and you say, all right, whatever that transducer moves, we know that the breaker is operating correctly. We're going to define that is this distance. So, and then if you make an absolute measurement, the contact movement's equal to the transducer's movement, but you must make sure that that transducer is calibrated, and then the electrical length or angular span of that transducer is calibration quality, and it doesn't depend on the measurement channel of the analyzer. And of course, the analyzer kind of establishes a scale factor. It's digital, so many pulses per millimeter, pulses per degree, or if it's like an analog, millimeters per volt, and something like that. So the other thing, of course, absolute measurement with a linear conversion factor. So now we go through calibrated transducer, make a measurement, then you just do a simple multiplication. And you can, as I said, do angle to angle or distance to distance, or if you saw that SF6 one where I hooked that dead tank breaker where I hooked up the angular transducer, you'll have, say, 1 degree is equal to 1.93 millimeters or 1.81 millimeters or whatever that manufacturer determines, but it's just a straight conversion. You don't need any kind of table. You can also have, or looking at this is an example where you'll see on the right you have your fixed contact, and on the left you have your transducer, but because of this pivot point, you actually have to multiply it by the ratio of L2 over L1 to convert your actual stroke correctly. To multiply that transducer, whatever it moves, your contact's actually moving a little bit more. We can also do a conversion where we hook up a rotary transducer directly to, like, the center of this moving contact. The actual contact path is following along an arc. And so now you have to multiply to get that arc length to see what your interrupter stroke is. And this is that SFA circuit breaker I mentioned before. So this is a 500 kV circuit breaker, 4 breaks per phase. And what you do is you'd open up these tanks, of course, evacuate the SF6 gas and hold it and everything during testing. But you'd open up these tanks and then hook that transducer right on the center there, and then that transducer would rotate along with these that interrupter. But what you want to do is convert that rotational value to a linear arc length value to get that interrupter actually moving back and forth on the left there. So the other thing, that's when you have a constant conversion. But you can also have it where it's not always constant through there. You might say, hey, at one point in these first couple of degrees, 1 degree is equal to 2 millimeter. Then as we start going up, 1 degree could be equal to 3, 1 degree 7, and so on. So we actually need a table to account for each little change throughout the entire stroke of this circuit breaker. An example of this, you can see here, where we have a fixed contact on the top, and then you have your moving contact, and we have this angular transducer, and now it's going to be, as I'm at the top and the bottom of this circle, like we'll say 0, and we'll call 0 degrees at the top of the line and 180, it's going to be moving that contact the most, but whereas we're at like a 90 degree or a 270 degree, it's going to have, the more that transducer moves, the less the contact will move. So you actually need a conversion table to measure this. So looking at this, what types of parameters are needed for proper measurement? You want to make sure your transducer is calibrated. You need to find out, do I need a conversion constant? Do I need a conversion table? So whatever I'm measuring, I can compare it back to my stroke. And then you want to get your speed calculation points. As I mentioned before, we're not just trying to get the stroke and over travels, which are important as well, but we want to know the velocity of this circuit breaker. And then also, if you do have some information about the stroke of the contacts, it's very beneficial because that's the first thing I always check. If my velocities are weird, I go in and I'll see, hey, what is the stroke of the breaker? Am I measuring that correct stroke? No, I'm not. Okay, something's going on here. Or yes, I am. Let's see if we're got the wrong speed calculation points, or if this breaker is just operating slowly. So that's kind of an intro to the different types of transducers and some different connections. So now what I want to do is look at a case study I did here on just a 38 kV Siemens STS2 circuit breaker. I'm sure a lot of you guys are familiar with this out there and have seen it. This one in particular, 1200 amps continuous current, 40K fault current. It's got your FA2 spring mix. It's an SS6 dead tank circuit breaker, 1 break per phase, gang operated. And just a picture here of the breaker itself, the control cabinet, and then on the right you'll see is the mechanism. Just for quick reference, this isn't the best picture. Nameplates are always hard to take pictures of, but this is just the nameplate of that particular circuit breaker that I did the measurements on. So what we did here is we looked at this breaker. The manufacturer, they recommend hooking up a transducer and doing a direct connection to the mechanism using a linear transducer. And they also tell you in the manual that 80 millimeters of transducer stroke is equivalent to 120 millimeters at the contact. So you actually have to multiply this, whatever you get with the transducer, by 1.5 to get the actual value of the contact stroke. And then they also tell you that the speed calculation points are based on, for the close, they'll be on contact touch in 10 milliseconds before that, and then contact separation in 10 milliseconds after. And if you take contact separation is right when the arcing starts, and then 10 milliseconds after, that's really, from a 50 hertz perspective, that would be one half cycle. So from a 60 hertz, really, you're a little over 1/2 cycle there. But you're right in that arcing zone of the circuit breaker. And throughout this case study, I'm going to refer to that connection as linear A, because this is on the closest to the it's on the mechanism, which is closest to the A phase. What I'm going to do, though, is we're going to make some additional connections, and we're going to use a linear transducer at the end of the operating linkage near phase C. So we're going to refer to this as linear C throughout the presentation. And this actually is how the manufacturer recommends that you hook to their more recent design of circuit breakers, is now hooking up to here. And so we can use a different transfer function or conversion table for those. And then additional to these 2 linear transducers, I'm actually going to, or we hooked up 3 rotary transducers as well. And what I did is we put these on each spline on each phase, and we're going to call it rotary A, rotary B, and rotary C for A, B, and C phase. And then we'll use the same speed calculation points for these as well. So looking at this one, from our manufacturer recommendation, we're going to call it linear A, and they say hook directly to the mechanism. So they provide, if you look on this very left picture, you'll see they provide a little spot that you can take off a plate below the control cabinet, so you can C-clamp up your mechanism there, sorry, your transducer up there to the cabinet. So you see on that second picture from the left, that's where it's C-clamped up, and you'll see a rod going up and hooking directly to this mechanism that drives up and down as that mechanism is going, that drives the interrupters in and out. And so we're going to measure there and then convert that value over to a linear value, or over to the value of the interrupters there. So that was linear A, the manufacturer's recommendation. And looking at this one, we'll call it linear C because it's close to the C phase. So now at the very opposite end of this circuit breaker, or end of the mechanism, you have all 3 phases are driven by these linkage rods. And so we're at the very end of that linkage rod. And so as that moves back and forth, we're going to measure the stroke there. And of course, we'll need to convert this as well, because it's not a direct connection to the interrupters either. It's actually 90 degrees to the travel of the interrupters there. Once again, we'll call this linear C throughout the presentation. And then additionally, even though the manufacturer recommends linear ones, we're going to hook up some rotary ones. And so you have one hooked up to A, B, and C phase. You'll see I took off the housing, and underneath there's the spline. So as that linkage rod drives in and out, it rotates the spline, which then we go from linear movement to rotary movement, and then that rotary movement is converted back to linear movement inside the tank housing and drives it back and forth, drives the interrupter back and forth. So what we do is we have an attachment we can provide to hook up to those guys, and you'll see it's hooked on all three, A, B, and C phase there. And then coming through here, you'll see what I was talking about over at the far right is the control cabinet, and that actuating rod's coming out. And then all three of our transducers are hooked up there. And I just don't have the wire going to the transducers because just to clarify the picture here. And then on the very upper left, you can see the rod going out that's going to that linear C transducer. So went through, made a measurement with this guy, and you'll see, okay, three completely different motion measurements. Although we have all three of our times are fairly close. You have 48.2, 47.9, 48.0. So really a difference between phases is only a third of a millisecond. But looking at motion, those are all quite different. We'll see 78.9 for linear A, 59, and it says millimeters, but just what I did on this is I decided that 1 degree was equal to 1 millimeter, just to make it a little bit easier. And then stroke C, you'll see, is 106.5 millimeters. So all three times are correct, but we have very different strokes. And of course, from this, we're going to get very different velocities as well, 2.81, 2.23, 4.07. So it looks quite odd if you compare all these. And then, and I will mention, I'm not using no conversion factors here. I am just making a direct measurement. And then once again, open operation, you'll see all three close times are very, very close. So you have actually 3/4 of a millisecond difference between phases. It's still pretty close. But stroke, once again, almost 80 millimeters, almost 60, and 106. So they're all quite different still. So looking at this, no conversion factors applied. Linear A, transducer stroke 78.9 millimeters. Rotary B, transducer stroke of 59 degrees. And then linear C, transducer stroke of 106.5 millimeters. So very different. If I went out here and I made a connection, and then say Jamie made a different connection, we both get totally different results here. But now we come through, and let's look at what the manufacturer said. They said, okay, measure here, connect your transducer to your mechanism, excuse me, connect your transducer to your mechanism, and then the 80 millimeters of movement at the transducer is equivalent to 120 millimeters at the contact. So really you need to use a conversion factor of 1.5 millimeters per millimeter. So if we look at this, our contact stroke is 118.35 millimeters measured here. So if we go through and do a slow close operation or slow open, you'll see that's the total travel distance of that interrupt. Now, looking at the rotary, so we measured it to be 59 degrees, and so at 118 millimeters, you see that if we use a rotary transducer, we really have a conversion of 1 degree is equivalent to 2 millimeters, so 2 millimeters per degree here. And then if you look at linear C, once again using that 118 as a base, and we measured 106, you'll see you get roughly 1.1099. And if you look at the modern manuals of these breakers, they'll actually say that 110 millimeters of movement at the transducer, if you hook up at this linear C point, is equivalent to 120 millimeters of stroke at the interrupters. So now let's go back and apply these conversion factors to our measurements. So now I went through and I applied a conversion factor to the three different phases and measure again. So looking at this, we now have lining all three of these up again, linear A, linear C, and rotary B, once again, times are all fine with a difference of 0.175 milliseconds between the three different close times. And now the strokes are all relatively the same, 118.1, 117.9, and 118.1. And you can even see, looking at these, they all pretty much follow the same deal. And if I overlay them all, you'll see that really it pretty much looks like the same stroke, except for you'll notice that there is some vibration on that linear A. So as that goes back and forth, it's kind of a little bit shaky there. And I would say that is due mainly because this one's hooked directly to that mechanism. So as that mechanism goes, it shakes this thing pretty violently. And then if we look at the open operation, once again, all three times are relatively close, within 0.825 milliseconds to each other. And then, excuse me, and then looking at the strokes, we vary 118.0 to 118.4 millimeters as well. Overlaying them, you'll see once again they all look very well, and even there's a little bit less vibration here on that linear A as well. So comparing a linear A, a rotary B, and linear C, you'll see that the strokes are all very similar. On the closed, the max difference is 0.2 millimeters. On the open, the max difference was 0.5 millimeters. And then the velocities were different on each phase, with a maximum difference of 0.5 meters per second, which is really approximately 10%. So I would say part of this is due to the oscillation or the motion on the trace A there, and there could be some flex in the travel rod as well. But looking at this, and I'll mention, I'll show on the next one too, that you have a little bit of variance because if all three contacts aren't timed sequentially and our speed calculation points are dependent on time, you will be measuring on different parts of the curve. But if you look at this, you'll see that really the transducer type and location doesn't have an effect on the results as long as you're using the proper conversion table and you're taking that into account. You're going to get similar results whether you hook up with a rotary, a linear, on this side of the breaker, on this side of the breaker, on the mechanism over here. You're really going to get pretty much the same thing going through. So now what we're going to do is we're going to look at our rotary A, B, and C. And so if you look at this, you'll see once again the close times, strokes, speed, all this is penetration over travel rebound. They're all very similar. I will mention that if you look at that B phase, that motion B, that black one in the center, there is some variation in there. And I'll talk about that a little bit in a minute. But looking at these, all three are pretty much similar values, 117.2 to 118.2. It's only a millimeter different, similar times and everything. But now we chose any one of the three connection points, and we were fine. So if I overlay these, you'll see it's almost the same. You would almost think that I'm just looking one measurement after another and comparing them, and they're overlaying right over each other. But what I do want to mention, if you look at the speeds here, you'll see the closed speeds 4.44 meters per second for A, 4.18 for B, and 4.36 for C. So they are a little bit different, but if you remember, the speed is based on timing. So what we look at is we say, okay, right here, our speed calculation points are these dots that you see kind of in the center of the curve, and those two lines coming down, you'll see one's right at contact touch, and then the other one's 10 milliseconds before, because that's what the manufacturer recommended for us. And then if you go through, you'll see those right there, but we can change these. Instead of referring to time, because we do have slightly different times for each of the three phases, let's actually refer and just put these below close. So if I look at this and I say, okay, 22 millimeters below close and 45 millimeters below that upper point, now you'll see our close speeds 4.34, 4.23, 4.29. So they're all pretty close to helping each other out there. Excuse me. So they're pretty much on top of each other once we get rid of that time-based reference for speed. Looking at the opens, once again, times are good. Strokes, now only 0.3 millimeters of difference between them. And then over travel, rebound, wipe, all that's the same. But once again, open speed, we vary from 4.5 to 4.7. So not as bad as the other one, but still some kind of variance. But, and that's because, once again, you see the dots here are all a little bit off because of that 0.65 milliseconds difference. We're going to be measuring on different parts of the curve. So if I switch over and go to speed calculation points, 22 millimeters below close, 45 millimeters below upper point. And the reason I chose these is because that's right in that same marking zone. But now you'll see 4.63, 4.64, and 4.57 milliseconds. So all very close there. So looking at this, what have we learned from the conclusions for rotary A, B, and C? The strokes were all very similar, with the max difference of 1 millimeter on the close and 0.3 millimeters on the open. And the velocities were different on each phase. So a little bit, approximately 5% difference, but this is, of course, because the times were slightly different. If we switched it down to like a certain part on the curve, and so it was shifted a little bit according to time, you'll see that we got them within 2.5% of each other. And there can be a little bit of play in the linkage. That one on the A phase is closest to the mechanism, so it probably is going to be traveling a little faster. That B phase is now in between, so you have a linkage pushing that B phase, then it catches the other linkage and it's got to drive C phase, so it can have a little bit of play there. And so you can expect a little bit of difference between those. But once again, transducer placement really doesn't have effect on, or it has kind of a small effect on the overall measurements there. I would recommend, though, if you're doing this, either place on either side of the linkage, either the A phase or the C phase, just to eliminate that play on the B phase there. So I think we're winding down on time here, but a couple of things I want to go through is, I've showed you multiple different connections. I've showed you that you can use a rotary, you can use a linear, and as long as you're converting correctly, you're fine. But what should you do when no information is given? You always want to talk to the manufacturer, consult with the manufacturer, look in the manual, and get whatever information you can. But if you can't, you want to go through and make the best decision you can for that transducer. So if possible, connect directly to the contact or actuating arm using a linear transducer. This way, an actual stroke will be measured, stroke velocity, all that stuff will be comparable to the manufacturer. And then from there, I do want to mention one thing. Don't place the transducer amount in direct path of moving parts. Be aware of where you're hooking this thing up. If you're not sure, a lot of times what I might do is hook up the transducer and then have it in one state, in the open state, then unhook the transducer, change the breaker state, and hook it up again and make sure that I didn't overrun on my stroke with a transducer or anything like that, and nothing moved in the way of that transducer. And once again, be safe on this. There's a lot of energy. Make sure that your mechanism is blocked from operating or in an open position before you operate that. If direct connection is not possible, you want to connect as close to the contacts as you can with minimal linkage between the connection point and the contacts. And here you can use a linear or a rotary transducer, whatever is easiest for you to hook up. And then you need to create a conversion factor or table. You can use drawings to create this. You can use a stroke and assume a linear relationship. That can be less accurate. And one thing, if you do this, you want to make sure that the circuit breaker is in good condition. And if you don't know the conversion table, you can measure and just trend this for future comparison, but make sure you're assuming the breaker's in a good operating condition when you do this commit, like hopefully on commissioning, or you do this kind of reference or fingerprint measurement. Once again, don't place the transducer and mount in direct path of moving parts. So speed calculation points, if the manufacturer doesn't give you anything, you're going to look for something on the linear portion of that contact stroke and something in the arcing zone of the contact. And then we recommend, if you have nothing else, contact touch in 10 milliseconds before for the close, contact separation 10 milliseconds after for the open there, because that's in the arcing zone. And most important here, once you use the transducer, conversion factor, speed calculation points, all this, use it for the life of that circuit breaker, because you want to be comparing and trending the same stuff over time. So preferably do this in known good condition, especially commissioning. Even if you have the manufacturer come out and commission that breaker for you, it might be good to go out and get your own measurements just for future reference data as well. So a couple of things. Time and travel analysis is critical. Not only time, but travel gives you over travel, it gives you stroke, it verifies the dash pot's working, and verifies that the velocity of those interrupters is correct. For transducer placement, first check the manual. Hopefully, a lot of times there's a diagram in there. They tell you a conversion factor if you need it. They tell you speed calculation point. If that's not in the manual, call the manufacturer. Talk to them, see what they recommend. And lastly, if not, choose an appropriate location on your own, directly connection to the contacts or actuating arm if you can with the linear, so you have a 1-to-1 ratio there, or use a linear and rotary to connect to as close to the contact as you can with the least amount of linkage in there, and then you want to create a conversion factor or table in trend there for future comparison. But as we learned from that case study, placement's not critical if you're using that proper conversion factor. And once again, once this method is chosen, continue to use it over the life of the TV. You might be using the wrong connection or not manufacturer's recommendation, but if you go through and you do this and hook it up and you're trending your results, you'll still have valuable data from there. So a couple of things, and we'll get to questions in just a moment, but I just wanted to show a couple of our products. The Eagle is our kind of intro to circuit breaker analysis. You can use it really in 245 kV and below. It's good for your oil circuit breakers, your gang-operated SO6, your vacuum circuit breakers, because this guy handles 1 break per phase and gang-operated, one motion measurements there. If you actually need 2 breaks per phase or you need 3 motion, you can upgrade to the TM1700. And this thing, we've operated, 765 kV substations and below. It'll work fine in any of those. So gang-operated IPO, oil circuit breakers, SO6, vacuum, GIS circuit breakers. And one of the unique features of the TM1700 is our ability to do DCM dual ground testing and measure a breaker with both sides grounded. And then, of course, if you need more than that, if you end up having old air blast and you need 4 breaks, 8 breaks, 10 breaks per phase or more, the TM1800 will do it for you. So this thing can test any circuit breaker out there, OCBs, SO6, vacuum, GIS, air blast. It also has the ability to do dual ground testing. It's kind of the Cadillac of circuit breaker testing out there. And this presentation is on transducers, so of course we offer a variety of transducers. We have our OCB kit, which is a nice long stroke length, a 500 or 600 millimeter transducer with your rod, your mounting kit, a clamp to mount, and everything, and a nice travel case there. We also have little ones, as I said, this 1-inch transducer for your vacuum circuit breakers. We have single phase and 3-phase, so what we call SS6 kits, which are shorter, your 300 millimeter transducers. And you see right here, clamp it up. You have your rod there. You can slide that back and forth to adjust your length, and we provide 2 different rod lengths, and so you can adjust with those. We also, of course, have rotary and a nice rotary kit, magnetic mounts, flexible arms, flex couplers, different bolts and attachments. And then we have some specialized transducers, your AHMA and your HMBs for those ABB ones. And then you'll notice, if you remember on that case study, I used this attachment that's also used for ABB, HPL, BLGs, Siemens live tank breakers as well. But this is a nice flexible piece that I used on a dead tank one. So for more information, thank you, of course, for attending this, but you can also look, excuse me, in our circuit breaker accessories guide. There's a link here, and I believe you should be able to, you view the recording, be able to click on that. We also have various like circuit breaker testing guide and application notes. So you can always go to Megger.com support and see our application guides in our technical library, or see our testing guide in your technical library. And of course, always feel free to contact your local Megger sales representative in case you have questions on a particular breaker or particular attachment and different things like that. But we have a lot of resources on the website and through us directly as well. So a couple things. Here's kind of the contact information if you want, and you'll see that you can contact me directly in sales as well there, and I'll let, right here I can let Jamie take over as well, I believe.
Yeah. Thank you, Robert. At this time, the presentation portion of the webinar is officially concluded. We will now take about 30 minutes to answer as many questions as possible. If you haven't already submitted questions, please submit them now into the Q&A box. For those that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue improving future webinars. Also, if you're interested in a demo or quotes on any of the products Robert just spoke about, there is a place in that survey to request a demo or quote, so please just let us know. A recording of this session will be available on our website at megger.com/webinars, and that'll be up probably in the next week or so. That webinar page will also contain the schedule for all upcoming webinars in 2017 and recordings of all the previous webinars. So, all right, let's go ahead and get to some of those questions. I'm going to be reading those off, and then Robert will answer them as soon as he can. All right, one of the first questions we got was from Patrick. It was earlier on in the webinar. He asked, can you give some additional information on over travel and rebound as to how much is acceptable and how much is allowed before I become concerned with these values?
Generally, it's hard to say as far as a percentage. It's usually, the manufacturer should specify something. So a lot of times you'll see like, hey, the strokes may be 110 millimeters, and so the maximum rebound might be 5 millimeters or so. You'll also see that they'll say I've seen some people where they have a maximum dynamic over travel or something, so they'll say the stroke plus total travel cannot exceed 113 millimeters or so. So there's not any general like IEEE or IEC or any recommendation for overall percentage. But what I've generally noticed is I'd say as you're starting to get from the 5 to 10% range on the over travel, you're starting to go too far, and you want to start monitoring and look at that dash pot. The other thing to do, of course, is look at your original measurements and see, okay, if we had an over travel before and it was 5 millimeters, and now we're starting to deviate, and we're getting, I'd say, within 50 to 100%, you're almost doubling that. You're starting to your dash pot's starting to go bad. So you want to investigate that as well. And I'd say as over travel, which is maybe 5% to maximum 10% is pushing it for sure. As you're starting to get over 5%, I would say rebound maybe half that. You can over travel some. As you're starting to rebound, it's a problem as well, especially for vacuum circuit breakers, because now those contacts are touching, and if you rebound, you can have quite an arc there. Whereas like an SF6 circuit breaker, as those contacts make, say you have 25 millimeters of white there, or contact penetration. If you have a 5 millimeter rebound or a 10 millimeter read on, you're still connected, so you don't have any kind of issue with arc or restrike, whereas with a vacuum circuit breaker, that would be a significant opening, and it could cause issues during operation or during interruption. All right.
Okay, thanks, Robert.
Yep.
Another question from Patrick was, are there differences that I should be concerned with regarding live tank breakers versus dead tank?
Not generally. What I found is that I left the screen there. What I found is that it really doesn't depend on the type of breaker. I've seen where you use a linear transducer on a live tank, a linear transducer on a dead tank. I've seen her use a rotary transducer on a live tank and the rotary on a dead tank. It really just depends on the manufacturer. And you'll even look at that case study I did with the Siemens. The manufacturer recommends using a linear, but we use the rotary and we were able to get very good results. So it doesn't really matter. It's generally whatever's easiest to connect and what information you have. If the manufacturer recommends one, go with theirs. If they don't, I would say then go whatever's easiest for you to connect to. But it doesn't matter. I would say normally the general, it seems like more the dead tank side are using linear transducers and the live tanks are using rotary, but there's exceptions to that as well. So it's hard. You really just have to evaluate it. But it doesn't matter as long as you're making a connection and converting that value correctly. So, all right, next question.
Okay, this question was from Felix. He asked, how do you figure out contact bounce from the travel diagram?
So actually, so this is, I get this question a lot because people think bounce is actually from the motion. What bounce actually is you get it from the timing. So a bounce specification, you can not hook up transducer at all and still get a bounce. Because what the IEEE IAC definition of timing is from contact or from closed coil energization until the first metal-on-metal contact. So the first time those contacts touch is when you measure your closing time. But a lot of times those contacts will touch, and say in the case of a vacuum breaker, they might touch and then bounce open slightly. And what we do is we record from when that first contact touches to when those things stay, then they open up, and we start recording that time until they come touching again. And so that, and remains touching or remains closed. And so that difference in time is actually what your bounce. So your bounce is generally measured in milliseconds. Where some people are thinking a bounce it's actually your rebound, like that over travel and then it comes back and you get your rebound. Sometimes that gets confused with bounce. But bounce is actually a time measurement from that first contact touch to contact separation to resting in that touch position. So I hope I made that clear. You can resubmit a question if it's not fully understandable.
All right. Another question from Patrick again was, is there a standard on how often the transducers should be calibrated?
No, generally, what you do is you make sure, like for our equipment, like our analyzers, we generally recommend calibrating once a year. But I've seen people not calibrate them for years because everything's working fine on it. The transducers themselves, usually, like especially if it's a digital, it's so many pulses per degree or pulses per millimeter. So once you know that value, you don't really need to calibrate them again. What I have seen is sometimes with your analog transducers, you have this resistor. It's a mechanical device, so it's sliding back and forth, and eventually it wears out some. as far as calibration goes, generally what I do is I look at the motion and I see, hey, everything's looking fine. We're getting the proper stroke, what we're expecting. So I'm not that worried about calibrating. If I'm a manufacturer and I have my ISO certifications and all that, they'll generally try and calibrate their transducers once a year. But as far as field goes, I don't see as many people calibrating them that often, and there's no quite standard telling you should calibrate these things once a year. Because generally you'll look at the measurement and you'll see, hey, this is what I'm expecting or what I'm not. And what's nice is you're measuring your times, your strokes, your velocities, and all that. So if everything's in match, you know that your transducer's calibrated and working well.
All right.
Next question, Jay.
This question was from Steve. He asked, when you refer to a conversion, to a conversion factor for the transducer, I think I've heard it called the transfer function in regard to CB testing. Have you heard that before?
So yeah, and so a couple of things. There's the calibration of the transducer that tells you like degrees per pulses per degree, pulses per millimeter, or volts per millimeter, whatever. But then there's you'll hear the term conversion factor, you'll hear the term conversion table, or you'll hear the term transfer function. Like you'll look in the manufacturer's manual sometimes and they'll say like the transfer function for this is like I'll see one and it'll be like a tangent function or a sine function. So they're all kind of the same thing. Like if you have a direct connection, you don't need it, but conversion table, conversion factor, transfer function, they're all referring to the same thing, how to convert generally an angular measurement into a linear measurement, or multiplying a linear measurement to another linear measurement because you're not on a direct connection.
Okay.
All right.
Another question was from Jonathan. He asked, should the transducer be calibrated on a certain interval? And if so, what is the recommended interval?
So this is the same thing that we kind of previously answered. Is you really, there's not like a standard one. If you're really worried about it, our standard is once a year or so. Like if I was a manufacturer and you're pumping out 10,000 breakers a year, you're operating that transducer a lot, so they're probably going to calibrate once a year. If you're in the field use, you can, once your transducer is calibrated once, if you're looking through and you're getting your good measurement and everything's going through, I generally don't calibrate that often, maybe every few years or so, 4 or 5 years, or if I just see a bad operation. First, whenever I see bad results, I assume I did something wrong first, check all my connections, then I assume my equipment's wrong and verify that if I can, move a transducer around or swap it out. And then lastly, I start looking, hey, something is wrong with this circuit breaker, just to see. But as far as calibration goes for field use, it's not that, once you verify that original calibration of the transducer, you're not doing it that often. Maybe, but I'd say 4 or 5 years would be fine.
Okay. Next question is from Larry. If one of my poles has burnt away or I have excessive pitting, what will my chart show, and is delta time shown? And in parentheses it says time between first and last pole contact.
So on what you'll do is, so you're making this measurement here, and as far as timing goes, you're going to hook up to each individual phase, and you'll measure the time of each individual phase. So, and what we're actually, let's look at an SF6 circuit breaker. What we're actually measuring is not the main contact. We're actually measuring that arcing contact, because that's the first metal to touch and the last metal to separate during our timing. So if that arcing contact does wear away, and say it was originally a length at 20 millimeters or so, and now it's down to 10 millimeters, you could see where that one phase is operating a little bit slower than the other ones. And we calculate the difference between phases for you, but you can also look at the 3 times yourself. And so you'll show up and you'll see, okay, a little bit. The problem is this breaker's moving so fast, so it might only be a millisecond of difference, and we allow a couple milliseconds to change there. Usually like the 2 in the open, and I forget what IEEE says, it's like 4 or something on the close. If you're really worried about your arcing contacts and the pitting and the bad connection, this is why you would do that thing we mentioned earlier called the dynamic resistance measurement test on your SF6 circuit breakers, because you'll see that arcing contact shrink, and if the resistance value is going up, you can compare to previous measurements and see that something's going on, and that arcing contact is wearing away prematurely, I would say. All right, Jimmy?
All right. Another question is, based on your experience, is it possible to use a linear transducer on live tank circuit breaker?
It depends on the circuit breaker. I have seen it used. If it's a live tank, a minimum oil circuit breaker, then that was generally what people would use. On the SF6 style live tanks, more often than not, I see a rotary transducer used on those. But you can hook up a linear if you would like. The problem is you might not be able to get to a good spot. But a lot of times what happens is you'll use, like on a live tank, you'll hook up a rotary to the base of that pole, and then it'll transfer to a linear movement and driving the interrupter up and down. Well, if you had access and you could get a little bit up on that linkage arm, you could hook a transducer there, clamp it down to it, and drive it up and down. So you can use a linear, but a lot of times the space and getting it in there isn't always the easiest to do. So it just depends on the circuit breaker itself. But if you look at it mechanically and can fit it in there, you can use it. It's just generally the rotaries seem to be more often used for your live tanks. The problem, of course, is you need that conversion factor or conversion table. All right, next question.
Okay, next question was from John. Your transducer kits have 3-phase and single-phase. When would you be required to perform 3-phase rather than single-phase?
So, and I'll say I that's kind of the way we name those is not the best. Really what they should be called is a gang-operated and an IPO. So generally if you have 245 kV circuit breakers and below, they usually have one operating mechanism that operates all 3 phases. So you really want to use one transducer per operating mechanism. So if it's a gang operated, you just want that single, we call it single phase, but really it should be called a gang operated kit. Now, when you get to 365 kV and above, the mechanisms don't have enough energy to be able to drive all 3 phases and interrupt all 3 phases at the same time. So now you have a separate operating mechanism per phase. So we call that an IPO, or independent pole operated circuit breaker. So now you hook up a transducer to each mechanism or each phase, and you measure all 3 of those. So really it should be gang operated and IPO kits, but we just call it single phase and 3-phase kit. And
okay.
one more thing I'll mention on that one is, as I said, generally 245 kV and below, it's gang operated, but you will see special applications where you're doing synchronous switching, such as capacitor banks or reactor banks, where you need to close on zero crossing or open on zero crossing. So you'll actually have all three phases with their own mechanism. Even though you could gang operate them for a regular transmission breaker, you might want to do, you might have three mechs here, and in those cases, once again, you'd want an independent transducer for each phase. All right, go ahead, Dean.
Thanks, Robert. Next one was from Gary. If no information is given where to measure speed, is there a way to estimate the arcing zone?
No, and as I said, what I recommend from what we've seen is if no no information is given, you want to go right at contact separation is where that arcing zone starts. So as those contacts separate, now there's no more direct connection, so you're going to have an arc going on inside that circuit breaker. So then you just go from there, and the reason we use 10 milliseconds is just from a lot of times from an IEC world, 50 hertz, and so that's half a cycle. So you could even do 10 milliseconds or 20 milliseconds afterwards. And if you think this breaker, it has a a 2-cycle, 3-cycle, 5-cycle interruption. So it's guaranteed to interrupt in there. But I would generally recommend doing contact touch in 10 milliseconds before, because it's kind of that previously to that touch. And then most important, of course, is the trip, contact separation in 10 milliseconds afterwards, because you're guaranteed to be in the arcing zone. It might be a little bit short, but that's really right there is when you're going to have, you want to make sure that your velocity is correct. All right, next question.
Okay, I think we have time for one more. Last one was from Otto. He asked, what are the advantages or disadvantages between digital or analog transducers?
A couple of things, and we'll talk about first linear and first rotary, but essentially there's no need. You can use a digital or an analog, and they're both sufficient. The one thing I'll say is with a digital transducer, you know that it can be a 200 millimeter transducer or a 500 millimeter transducer, but it's always going to have that same calibration of this many pulses is equal to this many millimeters or this many inches. Whereas an analog transducer, what you're doing is you're applying a voltage across the resistor. So now, if I'm using an analog transducer and I have a 500 millimeter transducer and I'm trying to measure a stroke of 10 millimeters, I really don't have a lot of resolution. Whereas the digital one, it'll be the same resolution across that. With that being said, I can take a real small, if I have a vacuum breaker, I can take a real small analog transducer, get it in there, and have very good resolution. So it's just you can choose which one you want, but analog versus linear doesn't matter. I'm sorry, analog versus digital doesn't matter on that. The one place where I generally recommend a digital one for sure is on your rotary transducers. Because the problem when you use an analog rotary transducer, it's a resistor. You can't keep spinning this thing around. You actually don't have a full 360-degree movement. And so it goes from 0 to 357 degrees, and then it resets itself. So if you're not paying attention and you hook up this rotary transducer, and it's right at, say, 340 degrees, and it's going to spin and go through that 357 and reset, your motion's going to be bad. So you want to make sure if you do use an analog rotary transducer, what I say is always measure it and put it at 50%. So that way, if it rotates one way or rotates the other way, it doesn't matter because you're not really going to be spinning around 180 degrees. So you won't have a problem measuring with that. The reason I like a digital is because I can just hook it up and it can spin around 10 times and it just keeps kicking out pulses, and it's not a problem. So as I said, there's no preference to either one. I would just say for rotary, for sure, I prefer digital. For linear, analog, digital, it really doesn't matter.
All right. Well, thanks again, Robert. Looks like that's all we have time for today. We do still have some unanswered questions that I will be forwarding over to Robert after the presentation, or after this concludes, and he will be getting in touch with you as soon as possible, hopefully next week. I want to thank you all for attending. We hope to see you again at one of our future webinars. Have a great weekend, and please remember to answer the survey if you can. Thank you very much.
Great. Thanks, Jimmy, and thanks everyone for attending. I appreciate it.